Hello friends, we have been discussing the various concepts of digital electronics in our previous discussions, and today we shall be talking about digital codes which form an important part of the digital technology. Many specialized codes are used in digital systems. Some codes are strictly numeric like BCD and others are alphanumeric, that is, they are used to represent numbers, letters, symbols and instructions. The codes introduced in this lecture are the Gray code and the ASCII code. The Gray code. The Gray code was designed by Frank Gray at Bell Laboratories and patented in 1953. The Gray code is unweighted and is not an arithmetic code, that is, there are no weights assigned to the bit positions. The important feature of the Gray code is that it exhibits only a single bit change from one code word to the next in sequence. Owing to this feature, the maximum error that can creep into a system using the binary Gray code to encode data is much less than the worst case error encountered in the case of straight binary encoding. This property is important in many applications such as shaft position encoders, where error chance increases with the number of bit changes between adjacent numbers in a sequence. Table here lists the binary and Gray code equivalents of decimal numbers from 0 to 15. Binary numbers are shown in the table for reference. Like binary numbers, the Gray code can have any number of bits. Notice a single bit change between successive Gray code words. For instance, in going from decimal 3 to decimal 4, the Gray code changes from 0010 to 0110, while the binary code changes from 0011 to 0100, a change of 3 bits. The only bit change is in the third bit from the right in the Gray code. The others remain the same. An examination of the 4-bit Gray code numbers shows that the last entry rolls over to the first entry, that is, the last and the first entry also differs by only 1 bit. This is known as the cyclic property of the Gray code. Although there can be more than one Gray code for a given word length, the term was first applied to a specific binary code for non-negative integers and called the binary reflected Gray code or simply the Gray code. There are various ways by which Gray codes within a given number of bits can be remembered. One such way is to remember the least significant bit follows a repetitive pattern of 2. The next higher adjacent bit follows a pattern of 4 and so on. Binary to Gray code conversion. Conversion between binary code and Gray code is sometimes useful. The following rules explain how to convert from a binary number to a Gray code word. Begin with the MSB of the binary number. The MSB of the Gray code is the same as the corresponding MSB of the given binary number. Going from left to right, add each adjacent pair of binary code bits to get the next Gray code bit. Discard the carries. The third most significant bit in the Gray code number is obtained by adding the second MSB and the third MSB in the binary number and ignoring the carry if any. The process continues until we obtain the least significant bit or the LSB of the gray code number by the addition of the LSB and the next higher adjacent bit of the binary number. Gray to binary conversion. To convert from gray code to binary, use a similar method. However, there are some differences. The following rules apply. The most significant bit, that is the leftmost in the binary code, is the same as the corresponding bit in the gray code. Add each binary code bit generated to the gray code bit in the next adjacent position. Discard carries. An application. A simplified diagram of a 3-bit shaft position encoder mechanism is shown in figure. Basically, there are 3 concentric conductive rings that are segmented into 8 sectors. The more sectors there are, the more accurately the position can be represented, but we are using only 8 for purpose of illustration. Each sector of each ring is fixed at either a high level or a low level voltage to represent ones and zeros. A 1 is indicated by a color sector and a 0 by a white sector. As the ring rotate with the shaft, they make contact with brush arrangements that is in a fixed position and to which output lines are connected. As the shaft rotates counterclockwise through 360 degrees, the 8 sectors move past the 3 brushes, producing a 3-bit binary output that indicates the shaft position. The sectors are arranged in a straight binary pattern so that the brushes go from 0 0 0 to 0 0 1 to 0 1 0 to 0 1 1 and so on. When the brushes are on color sectors, they output a 1, and when on white sectors, they output a 0. If one brush is slightly ahead of the others during the transition from one sector to the next, an erroneous output can occur. Consider what happens when the brushes are on 1 1 1 sector and about to enter the 0 0 0 sector. If the MSB brush is slightly ahead, the position would be incorrectly indicated by a transitional 0 1 1 instead of a 1 1 1 or a 0 0 0. In this type of application, it is virtually impossible to maintain precise mechanical alignment of all the brushes. Therefore, some error will always occur at many of the transitions between sectors. The gray code is used to eliminate the error problem which is inherent in the binary code. As shown in part B, the gray code assures that only one bit will change between adjacent sectors. This means that even though the brushes may not be in precise alignment, there will never be a transitional error. For example, let us again consider what happens when the brushes are on the 1 1 1 sector and about to move into the next sector 1 0 1. The only two possible outputs during the transition are 1 1 1 and 1 0 1, no matter how the brushes are aligned. A similar situation occurs at the transition between each of the other sectors. Alphanumeric codes. In order to communicate you need not only numbers, but also letters and other symbols. In the strictest sense, alphanumeric codes are codes that present numbers and alphabetic characters or letters. Most such codes, however, also represent other characters such as symbols and various instructions necessary for conveying information. At a minimum, an alphanumeric code must represent 10 decimal digits and 26 letters of the alphabet for a total of 36 items. This number requires 6 bits in each code combination because 5 bits are insufficient. There are 64 total combinations of 6 bits, so there are 28 unused code combinations. Obviously, in many applications, symbols other than just numbers and letters are necessary to communicate completely. You need spaces, periods, colons, semicolons, question marks, etc. You also need instructions to tell the receiving system what to do with the information. With codes that are 6 bits long, you can handle decimal numbers, the alphabet and 28 other symbols. This should give you an idea of the requirements for a basic alphanumeric code. The ASCII is the most common alphanumeric code and is covered next. ASCII is the abbreviation for American Standard Code for Information Interchange. ASCII is a universally accepted alphanumeric code used in most computers and other electronic equipment. Most computer keyboards are standardized with the ASCII. When you enter a letter, a number or control command, the corresponding ASCII code goes into the computer. A computer keyboard has a dedicated microprocessor that constantly scans keyboard circuits to detect when a key has been pressed and released. A unique scan code is produced by computer software representing that particular key. The scan code is then converted to an alphanumeric code for use by the computer. ASCII has 128 characters and symbols represented by a 7-bit binary code. Actually, ASCII can be considered an 8-bit code with the most significant bit always 0. The 8-bit code is 00 through 7F in hexadecimal. The first 32 ASCII characters are non-graphic commands that are never printed or displayed and are used only for control purposes. Examples of the control characters are null, line feed, start of text and escape. The other characters are graphic symbols that can be printed or displayed and include the letters of the alphabet, the 10 decimal digits, punctuation signs and other commonly used symbols. You can easily download a table listing the ASCII code showing the decimal, hexadecimal and binary representations for each character and symbol from the internet. Error detection and correction codes. In this section, two methods for adding bits to codes to either detect a single bit error or detect and correct a single bit error are discussed. The parity method of error detection is introduced and the Hamming method of single error detection and correction is covered. When a bit in a given code word is found to be in error, it can be corrected by simply inverting it. Parity method for error detection. Many systems use a parity bit as a means for bit error detection. A group of bits contain either an even or an odd number of ones. A parity bit is attached to a group of bits to make the total number of ones in a group always even or always odd, and even parity bit makes the total number of ones even, and an odd parity bit makes the total odd. A given system operates with even or odd parity, but not with both. For instance, if a system operates with even parity, a check is made on each group of bits received to make sure the total number of ones in that group is even. If there is an odd number of ones, an error has occurred. As an illustration of how parity bits are attached to a code, table here lists the parity bits for each BCD number for both even and odd parity. The parity bit for each BCD number is in the P column. The parity bit can be attached to the code at either the beginning or the end, depending on system design. Notice that the total number of ones, including the parity bit, is always even for even parity and always odd for odd parity. Detecting an error. A parity bit provides for the detection of a single bit error or any odd number of errors, which is very unlikely, but cannot check for two errors in one group. For instance, let us assume that we wish to transmit the BCD code 0101. The total code transmitted, including the even parity bit, is 00101, which consists of the BCD code and the even parity bit as shown. Now, let us assume that an error occurs in the third bit from the left, that is, the 1 becomes a 0. When this code is received, the parity check circuitry determines that there is only a single one, that is, an odd number, when there should be an even number of ones. Because an even number of ones does not appear in the code when it was received, an error is indicated. An odd parity bit also provides in a similar manner for the detection of a single error in a given group of bits. The Hamming code. As you have seen, a single parity bit allows for the detection of single bit errors in a code word. A single parity bit can indicate that there is an error in a certain group of bits. In order to correct a detected error, more information is required because the position of the bit in error must be identified before it can be corrected. More than one parity bit must be included in a group of bits to be able to correct a detected error. In a 7-bit code, there are 7 possible single bit errors. In this case, 3 parity bits can not only detect an error, but can specify the position of the bit in error. The Hamming code provides for single error correction. The following coverage illustrates the construction of a 7-bit Hamming code for single error correction. Number of parity bits. If the number of data bits is designated D, then the number of parity bits P is determined by the following relationship, where 2 to the power P is greater than and equal to D plus P plus 1. For example, if we have 4 data bits, then P is found by trial and error with this equation. Let P be equal to 2, then 2 to the power P is equal to 2 to the power 2 and is equal to 4, and therefore, D plus P plus 1 comes out to be 7. Since 2 to the power P must be equal to or greater than D plus P plus 1, the relationship in equation above is not satisfied. we have to try again. Let p be equal to 3. Then 2 to the power p is equal to 2 to the power 3 and comes out to be 8, and d plus p plus 1 comes out to be 8. This value of p satisfies the relation of equation. So, 3 parity bits are required to provide single error correction for 4 data bits. It should be noted here that error detection and correction are provided for all bits, both parity and data, in a code group. That is, parity bits also check themselves. Placement of parity bits in the code. Now that we have found the number of parity bits required in our particular example, we must arrange the bits properly in the code. At this point, you should realize that in this example, the code is composed of 4 data bits and 3 parity bits. The leftmost bit is designated bit 1, the next bit is bit 2, and so on as follows. The parity bits are located in the positions that are numbered corresponding to ascending powers of 2 as indicated. The symbol Pn designates a particular parity bit and Dn designates a particular data bit. Finally, we must assign a 1 or 0 value to each parity bit. Since each parity bit provides a check on certain other bits in the total code, we must know the value of these others in order to assign the parity bit value. To find the bit values, first number each bit position in binary, that is, write the binary number for each decimal position number as shown in the second 2 rows of the table. Next, indicate the parity and data bit locations as shown in the first row of table. Notice that the binary position number of parity bit P1 has a 1 for its rightmost digit. The parity bit checks all bit positions including itself that have 1s in the same location in the binary position numbers. Therefore, parity bit P1 checks bit positions 1, 3, 5 and 7. The binary position number for parity bit P2 has a 1 for its middle bit. It checks all bit positions including itself that have 1s in the same position. Therefore, parity bit P2 checks bit positions 2, 3, 6 and 7. The binary position number for parity bit P3 has a 1 for its leftmost bit. It checks all bit positions including itself that have 1s in the same position. Therefore, parity bit P3 checks bit positions 4, 5, 6 and 7. In each case, the parity bit is assigned a value to make the quantity of 1s in the set of bits that it checks either odd or even, depending on which is specified. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. We learned that the ASCII is a 7-bit alphanumeric code that is widely used in computer systems for input and output of information. A parity bit is used to detect an error in a code. The Hamming code provides for a single error detection and correction. So friends, that is it for today. See you in the next lecture. Thank you very much.